So I will now start to tell you a little bit about my findings in experiments that I ran on supervised and unsupervised network. And I urge you to read as much as possible as the references that are included at the end of this lecture. So first of all, we really need to look at connections. If you are talking about unsupervised network, so we're talking about the clustering learning. Like we looked in previous lecture on clustering learning, remember that unsupervised techniques, they train filters, so they find the filters that will create this map from a series of input. But what about connections? So actually, usually you don't take just one input and convolve it by these filters. You might do that at the input layer, but you always have a combination of inputs that you want to use in order to combine the filtering operation into another set of maps. So there has to be some connection at each single layer, each layer of the deep network. There are a connection matrix, connection table that is quite important to really capture and represent well. So in theory, you would need to learn them from data as well. You want to learn this connection from the data. The data has to tell you how to do it. So I will talk a little bit in this second portion of the lecture about connection. It's something that has become apparent to me that it's quite important in deep network as well, especially when they're trained unsupervised. I want to remind you that in the case of supervised networks, the connection are learned by stochastic gradient descent or the learning technique automatically for you. But in unsupervised network, connection are quite important and they have to be learned too. If you look original filters about the sparse coding or unsupervised deep network, some of them might not be talking about this issue. And I think it's a very important issue actually. So generally, if you want to connect a set of input to basically the output of the second convolution or the second filtering operation in the next layer, so what you have is you have n maps that have to be first combined together and then convolved by the number of filters in the layer n+1. So what you can have is you can have this kind of connection tables between these two layers, one to one. So for example, you have n filters here and you have n maps on the next layer. You have n maps here and n maps in the next layer, so you can connect them one to one. You could also connect n to m. So for example, you could take a little subset, a small subset of these maps, add them all together, and then filter them by a combination of this. You could also do each one of these filters should participate in the output of all the second layer filter. So it's a one-to-all or fully connected network. Really, it shouldn't be one-to-all, but it should be all-to-all. Because you are really connecting every single feature to all the other feature in the next layer. Or we can just say one-to-all. As we said, if you're thinking about each one of this map, you know how is it connected to all the following maps. So one-to-one means one connection, one layer is connected only to another layer here. N-to-M means that n layer here are connected to m. So one layer here is connected to n of these layers, and one of these guys is connected to m of these features. And then there's one-to-all, where each one of these layers is connected to all the other ones. So that's really some of the ideas here. So let's think a little bit about these connections. One-to-one might be of limited use because one map is only propagating to one following maps. So you're kind of retaining the same information. There's a few neurons in the next few neuron maps really. In the next layer, use previous layer feature. So only one map here, the one map that is projected to, will use what you found in the previous layer. So it's kind of maybe not the best choice because you're not taking advantage of combining features together, and that's what you usually want in a deep network. You want to try to combine the effect of multiple of these filters into the next layer so that you can start creating groupings of features. The second option is end-to-end, and that's one of the most typical really, because it's fairly effective. So what you do is you try to take a combination of n layer maps or n inputs to create really m outputs. So this is really the most general connection. So each next layer neuron connects to n previous layer neuron, and they could be chosen at random. So typically some of these are chosen at random because at least in supervised network is because once you set this up, a supervised network will figure out what kind of filters he better connect together. In a unsupervised network, connecting things at random might be not really, again, one of the best options because you might be getting very different features in here, and trying to combine them together randomly, you might connect features that supposedly might not give you the kind of invariance that you want because they are maybe too different from each other or they don't appear in the data together. So what you really want to do for an unsupervised network is you want to try to get a few of these maps that co-occur in the data. They have to co-occur in the data, and these things that co-occur in the data, so they have to be sent to the next layer. So for example, you could look at this small patch and see from the data what kind of filters tend to occur together in each layer. And you could group them together, and that would form a group of n, and then you each one of these, the next layer would use one of these features, for example, or multiple. You could also do fully connected layers, so every one of these maps is connected to all the other ones. This is usually slower because of the large amount of computation you have to do, so you have to add each one of them to to basically compute each of the other maps. But you can also reduce previous strong layer features by averaging them. So if all the features are averaged together, maybe there was one of them that was really strong and should have been really pushed forward to the next layer, but because you're averaging with all of them, its output value is damped a little bit. And so that might be something to think about also.